Hi, everyone. Welcome back to E54. Today, we'll be going over lecture 13, where we'll introduce composites. So some of the main things we're going to cover are what are the different classes and types of composites, why we use these materials instead of just the raw metals, ceramics, and polymers that we talked about. How can we estimate things like the stiffness and the strength of composites? And then we'll also talk a little bit about typical applications, okay? So the idea generically is that we want to combine materials in different combinations so that we can get some different combination of properties, okay? A simple example could be use some of the flexibility and low weight of a polymer plus the strength of a ceramic. So really the generic idea here is we're using what's called the principle of combined action. So the idea here is that a mixture of materials will give some form of average properties. So we can start to motivate our study of these materials by looking at some simple plots. These plots both have density on the x-axis, and the left plot has Young's modulus, so the stiffness of the material on the y, and the plot on the right has the strength of the material on the y, okay? So what you can see here is that if you forget the x-axis for a second, and we just want stiff and strong materials, maybe we would always pick engineered ceramics, for example. But that's not always the case. We often do have to care about density, things, what's the weight of our sample. So for example, you can see that with some composite materials, we can get similar stiffnesses and strengths, for example, as metals and ceramics, but they're a lot lighter. Okay, so that's one obvious motivation. We'll talk about a lot of different terminologies and classifications today because we have to describe different ways of thinking about putting together different materials. So one of the things we'll have to introduce is this concept of a matrix. So our instinct is to say that the matrix is the most plentiful material, but that's not always true. But what it really is it's the continuous phase inside of our material, okay? And usually we start out describing our composites by describing that matrix. So for example, three large classes of composites are metal matrix composites, ceramic matrix composites, and polymer matrix composites. And all that is describing is what is the continuous phase. So what is our base material, and then we're mixing in something else, okay? And generally the desired sort of end goal is going to depend on what that matrix was. We're often trying to overcome some limitation of what that matrix is. So for metal matrix composites, we generally want to do things like increase the strength, either the yield strength or the tensile strength or true strength, and also things like the creep resistance. For ceramic matrix composites, remember, these are already strong, but we said that they're often brittle. So for example, we want to increase the fracture toughness of these materials. Polymers, on the other hand, we said that they tend to be more compliant and less strong. So we want to increase all those things over the base polymer. Okay. And we'll talk about a lot of classifications, things like particle, fiber, structural. And these are describing how we're putting in this second chunk of material to try to accomplish that goal. So the first thing we can look at is what are called geometric and spatial characteristics of that reinforcing phase. So in all these pictures, our matrix is drawn in blue. We haven't defined what it is. It can be a metal, a ceramic, a polymer, doesn't matter. And then our dispersed phase, our reinforcing phase, is in the orange, okay? So we can change the concentration. In this box, we're just showing these long tubes of the reinforcing phase, and in the bottom picture, we have about twice as much. Okay, so we've added more, so you can vary the concentration. You can also vary the size of these reinforcing pieces, so you can have small or large pieces. You can change the shape. These can be cylinders, they could be these rectangular shapes, they could be anything. You can change the spatial distribution. So in the top example, these orange cylinders are all aligned in one line. whereas in the bottom picture, there's some distribution. So they're sort of out of phase in the vertical direction. Go up a little bit, down. You can also change the orientation. So you can have the reinforcement phase or dispersed phase aligned in the plane of the material or coming vertically. So you can change all of these different features. So as a brief overview, a lot of these terms won't mean anything to you right now, but by the end of the day, we'll kind of have a sense of what they are describing. We can talk about the shape of the reinforcements. And then within any one of these categories, so we can talk about what happens when we have dispersed particles or large particles, for example. So we'll build up sort of multiple levels of describing these composites. What I'm showing on this image, we'll work our way through. So let's first start with particle reinforced composites. What I'm showing on this slide is 3 different examples, some that we've already seen. Now, the top one is probably the one that you remember the name, so spheroidite. We talked about this within the last few lectures when we were discussing phase transformations in steel. This was the sample where we had a eutectoid-like transformation happen, but we then heat treated the sample, allowed it to coarsen, and ended up with some matrix of a soft phase with that harder cementite phase in there. Okay, so this is actually a type of composite. So we have that ductile ferrite phase, that's continuous, that's our matrix. And then we have that hard but brittle cementite phase distributed in there. You can find lots of other examples. On the middle row, we're showing a tungsten carbide and cobalt composite. So the cobalt is the matrix, it's the continuous phase, it's light. And then these darker tungsten carbide particles are the reinforcing phase. In this case, it's something similar to that spheroidite. It's a ductile phase being reinforced by a brittle but hard phase. But the main thing I want to point out is that in this case, the matrix phase is only about 10 to 15% of the material. So again, it doesn't matter that it's less than 50%. What matters is that it's continuous and it sort of is filling in all these cracks. And then these are the dispersed particles. Another good example from our everyday lives is things like automobile tires. So the matrix is rubber, so it's something that's compliant, can have some give and can absorb some shocks. But for this application, we need it to be a little bit stiffer, so there's carbon particles that are mixed in. Other good examples that we're used to thinking about are things like concrete. So this is a composite that's made up of gravel, sand, and cement. You could ask the question, why sand and gravel? They're both basically forming as little rocks. And the basic idea is here, that's just difference in size. So the sand is smaller and it tends to pack into the voids in the gravel, so you can get a dense material. Even within concrete, different types of concrete are good examples of different types of composites. So reinforced concrete is concrete where we actually add in something like a steel rod or a mesh to strengthen our material. You'll often see this if you see a building on campus being constructed. You'll see that there's, before they pour the concrete, there's these little fingers of steel going up. Pre-stressed concrete is another good example. I'm showing this on the right here. So if you think about, you have your mold for your concrete, we put some sort of wire, or they call it a tendon here, and we load it up. So that's under tension. We fill and cast that concrete beam. And then if we release that load on the wire, it pulls back and puts this concrete under a compressive force. Okay. The idea is pretty simple. We talked a lot about cracks opening up when we discussed fracture. Well, tensile stresses open cracks. So if we put this under compression, it's better able to resist cracking. Post-tensioning is another similar type of idea. So here, you have a tendon through that concrete, and you can actually load this sample up by attaching something like a nut or a set of nuts at the ends of the side and clamping and sort of torquing them down. So for these particle reinforced composites, one of the simpler properties we can look at is the elastic modulus. So it's the stiffness of the material. And in this case, I'm showing some real data for copper and tungsten. So copper is relatively compliant, low modulus. So at 0%, this would be pure copper. 100% tungsten would be pure tungsten, so relatively stiff. We find as the data falls in between those two extremes. And what I've shown here is this basically plotting two different types of curves. So one is an upper limit. It's basically just assuming a linear relationship between the modulus of the copper and the modulus of the tungsten. The second one is showing what we can think of as a lower limit. It's saying that the inverse of the modulus is equal to the inverse of the moduli divided by or normalized by the volume of each of the phases, okay? What you can kind of see from this plot is that neither of these works all that well, but that they provide bounds for the data. So the data falls in between those points with some scatter. We haven't talked about these properties yet, but we're going to introduce in our next two lectures electrical conductivity and thermal conductivity. And it's just important to know that we could make a plot like this that looks very similar and come up with upper bounds and lower bounds for what those conductivity values would do. So the next type of composite that we'll discuss are what are called fiber reinforced composites. So these fibers are generally very strong, and we usually want to put them in to get a strength improvement in our material. A good example is fiberglass. So this is just continuous glass filaments in a polymer matrix. The strength is due to the fibers, and the polymer is there just to hold it in place. Within this class, we can talk about having different types of materials being used as the fibers. We can have what are known as whiskers. So these are generally thin single crystals with a large length to diameter ratio. So they're long, drawn out single crystals. Common examples are things like graphite, silicon nitride, silicon carbide. And the idea here is that because of that high crystalline perfection, they don't have a lot of pre-existing defects. They can be extremely strong. In fact, these are sort of the class of materials that are the strongest known. The issue is, though, you can imagine it's hard to make a really perfect material, so it tends to be pretty expensive. Another example of a common fiber material, or what we just classify as fibers. So these again have these long features, but they can be polycrystalline and amorphous, so it's a little bit simpler. Often we use things like polymers and ceramics, and good examples are things like alumina, some different types of glasses, boron. It's important to point out that it can also be something, your fiber can be also something simple like a metal wire. So a steel, molybdenum, or tungsten wire is a possibility. When we're talking about fibers, an important topic is the alignment of the fibers within the sample. So what we're showing here is a few different examples of types of fiber reinforced composites. The first thing you can notice is whether the label says aligned. So in these two examples that says aligned, you can see that the fibers are all organized in this vertical fashion, okay? Whereas in the random, they're sort of they're along all different axes within this chunk, okay? The other thing, and we're going to introduce this concept a little bit more rigorously soon, is that we can also distinguish between continuous and discontinuous fibers. The simple way to think about this is continuous is when these fibers are very long, and discontinuous is when they're very short, okay? And the reason that's important, and we'll see this in a slide or two, is that this greatly affects the properties of the material. Just as some examples, on the left, I'm showing a pure metal example. So if you have a eutectic solidification in this nickel 3 aluminum and molybdenum system, you can end up getting a composite structure. Your matrix in this case is the molybdenum, which is very ductile. So this is basically cutting through and seeing these chunks of this intermetallic come out. And that intermetallic nickel 3 aluminum is strong but brittle. You can also get a pure ceramic type of example of this. So this is a glass with silicon carbide fibers mixed into it. And the basic idea is that the glass has a much lower modulus than the silicon carbide. So they're putting the silicon carbide in to stiffen the material. If you take this composite and break it, you can look at that fracture surface. It has all these jagged edges. If we zoom in with a scanning electron microscope, we can see those little silicon carbide fibers poking out of that fractured surface. So if we're adding in a material to try to strengthen and improve the mechanical properties of our system, what we really want to make sure is that this fiber, this strong piece that we're putting in, can effectively be transferred the load. Okay, this little schematic is showing is that it's basically some chunk of your matrix with a reinforcement fiber in there. And if we think about taking and pooling on this fiber, what you'll see is in this region up here, the sample will share the load, and that's a good thing. So some of this material is being loaded, some of the fiber is being loaded. And in this bottom region, the load is just through the matrix material, which is not really what we're after. Okay. So a common thing to talk about is what's the critical length of these fibers. So we generally, if they're longer, that's better. And you can think about this as if we're above this critical length, we can assume that we'll be getting some effective strengthening. Okay. On the left here is an equation that describes how we can find this critical length. It's going to depend on some of the properties of that material. So it's going to depend on what's the strength of the fiber. It's also going to depend on what the size of the fiber is, characterized by the diameter. So if we have stronger fiber or a larger diameter, that critical length is going to have to go up. Another thing that matters is the fiber matrix bond strength. So how strong is that connection between these two different phases? Okay. Just so we have a rough sense of what we're talking about. So for a lot of glass and carbon fiber matrix combinations, so putting in some generic numbers there, this critical length is often going to be on the order of about 1 millimeter or so. To try to understand how this matters, what we can do is think about what the stress inside that reinforced phase would look like. Okay. So on the left here, this is something that's right at that critical length. Basically what happens is at the end of this fiber, where it meets just pure matrix, it can't really be sharing that load very efficiently. Okay. So what actually happens is the stress in this fiber will increase linearly until some maximum value and then drop. Okay. So it has to increase as we move across this fiber, reaches its maximum in the middle and then drops. Now, if the fiber is very, very long, this is a positive thing. So at the ends, it increases. It reaches the strength of the fiber. It can't be loaded any higher than that, or else it'll break. But the point is that if you have a really long fiber, you'll have a long middle region, which is holding stresses that are close to the strength of the fiber. That's really a good thing for having a strong material. If I contrast that with what happens with a really short fiber, so a really short fiber will have that same linear increase and then a linear decrease, but it's too small to be reaching anywhere near the strength of the material. So basically we're wasting a lot of the strength. So this gap that's right here is strength that the material has, but we're wasting it. Okay. So this kind of picture kind of tells us how we can define what is continuous and what is discontinuous. So if we're much larger than that critical length, so we're over here, most of our material or a big chunk of our material is holding stresses that are close to the strength of the material, or can hold stresses that are close to the strength of the material. That's continuous. That's a good thing. Discontinuous is if we're a lot smaller than that critical length. Just to show you an example, so this is on the right here is an example of a discontinuous fiber composite example. It actually has a dimensionality to it called random 2D. So this is actually just a mixture of carbon and carbon. What it does is it has an epoxy matrix, which isn't very stiff and isn't very strong. And then there are some aligned carbon fibers, so these lighter regions in this picture, which are very stiff and strong. The way this is made is it's built in sheets so that there's a sort of planar chunk of material. The fibers are aligned in that plane, and then they stack up different sheets on top of each other. Okay? This is commonly used in things like disc brakes in your car. Okay? But this is a good example of these fibers are small, so they're discontinuous. And we can, again, also mention the dimensionality of how they're organized inside of our sample. So I mentioned this concept of if we're above that critical size, it's continuous. If we're below, it's discontinuous. It's important to put an actual number on that. We really don't want to be just above that critical length. We want to be a lot above that critical length. So if our equation for The critical length is shown right here. We can do a bunch of experiments, try to see when we put in these fibers, when do we start to get a sufficient strengthening effect. And the sort of empirical rule of thumb is that if you want effective strengthening, you need to have fiber lengths that are greater than 15 times the fiber strength, the fiber diameter divided by the fiber matrix interface, okay? If you want to think about this, it's basically saying that your fiber lengths need to be about 30 times larger than your critical length. So this is describing when you can reach the strength of the material, but it's saying that you want to actually be a lot larger than that. Okay? So if before we said commonly that critical length is about 1 millimeter, that means what you really want, if you want to be effective, is have fibers which are about 15 millimeters or so. Okay? And again, the idea is that you have to think about the distribution of the stress. So you don't want it to change and be varying over large regions. You want to actually have most of your fiber, when we say it's efficient, it's carrying load in an efficient manner. Now, the strength of your material is generally going to be a trade-off between what the strength of your matrix and the strength of your fiber looks like. On the left plot here, it's just showing the matrix material and the fiber being, or sorry, the matrix and the fiber being tested independently. So the fiber in this case is very stiff, has a steep slope, it's strong, it breaks at a high stress value, but it's brittle. So it has a low strain to failure. The matrix has a different balance of properties. It's not as stiff, but then it has some yielding and can have some relatively good ductility. Okay. If we put these together, we'll find that our composite material is going to follow a curve that kind of looks like this green curve. Okay. It's going to load up with some modulus that's between or some value in between the two different phases of that's made out of. It will fail at some value that is less than the matrix, but you can also see that there's some discontinuities. So at this point right here, the matrix starts to yield and the slope of this curve changes. Okay? But the main point I'm trying to get across is that we have some sort of balance of the properties of the two phases we're putting together. So if we try to understand how we can predict what that strength would be, we can think about two extreme examples. The first is, what if we're loading our composite in what we call the longitudinal direction? And this means perfectly along the long direction of those fibers, okay? So let's say we have continuous fibers. They're long enough that they can effectively hold that force we're applying to the sample. If we have this type of deformation, what we're actually getting is something what we call isostrain. It means that the strain in the different phases, so the composite as a whole, the matrix by itself, and the fiber by itself are all the same. And we can use that to identify that the stress in the composite is going to be some combination of the stresses in the different phases multiplied by the volume fraction of each of those phases. Okay. If that's true, then the modulus can be expressed in a similar type of form. Okay. The modulus of the composite is going to be equal to the modulus of the matrix times its volume fraction plus the modulus of the fiber times its volume fraction. The other extreme example is if we think we have these long, strong fibers inside of our material, if we load it in the transverse direction, so instead of along the long direction, load it perpendicular to that fiber. In this case, we'll have an isostress condition. So the stresses in the total composite, the matrix, and the fiber are all the same. So we can come up with a different equation saying that the strain in the composite is going to be a combination of the strain in the matrix times the volume fraction of the matrix plus the strain in the fiber times the volume fraction of the fiber, and end up with this expression of what the transverse modulus of the composite would be. Hopefully you're recognizing that these equations that we're building up look like those upper and lower bounds that I was describing before. Okay. And in fact, that's what we were seeing. So this equation right here for when we're loading the fibers longitudinally is the upper bound. That's the best we can do. This equation right here, when we're loading them perpendicular, is the lower bound. That's the worst we can do. So we saw those upper and lower bounds for particle composites where they were just mixed in there randomly. So we didn't have any alignment of anything. So there's nothing you can get. Anyways, these same type of forms of equations also work for discontinuous fibers. So again, this is when the fibers are less than this value. And again, you can say that the modulus in the fiber direction is going to be equal to some equation that looks like just this rule of mixtures. The only difference is oftentimes for these discontinuous fibers, we have this factor K here. And all this is doing is saying, what's the efficiency of these fibers, okay? If everything is aligned in one dimension, that K could be equal to 1. It says, oh, everything's perfect. And this looks just like what we saw for the continuous fibers. It can be 0 if basically we're perpendicular and we're not getting any effect. But it can also be something intermediate, so between 0 and 1, where, for example, if they're distributedly randomly in a two-dimensional plane, but there is a sort of that planar alignment, okay? And we can also do something similar with the true strength in those fiber directions. So if they're aligned, it's just going to be a combination of the strength of those different phases. Sorry, the tensile strength of those two different phases. So just to show you how these things start to fail, I wanted to present a few different examples. On the left is an example of a material where there's some softer epoxy. It appears darker in this image. And then these things in the middle are reinforcement fibers, okay? They're sort of woven into the material. This is the undeformed case. If you go down to the bottom, this is when our sample has been pooled and broken. You can see some interesting features. So these light gray regions are where pockets in that epoxy formed. This is where that dark phase broke apart and ripped open. You can even see that the top part of this fiber has cracked and broken, but that the middle part has remained intact. So what you're seeing is that in the direction where these fibers were put in, the material is pretty strong, and even those fibers can remain intact after some heavy deformation. So with that in mind, you could think about weaving those fibers in at different angles, or even making, this is a side view of a sample, where it's woven in the plane and then also vertically, so in different directions. And I keep using this term woven because it actually looks, if you zoom in, it looks like weaving we see in fabrics and things like that. The difference being, instead of just doing something relatively weak like cotton that we use to make a shirt, they might use this with a very strong glass fiber, but the concept is very similar. And that fiber choice that you decide to put in can be very widely. So this is just showing a few different examples. So our general ranges of strength and modulus, so specific means it's normalized by the weight of the material, are down here in the bottom left corner. And you can get everything from relatively stiff with modest strength materials like a high modulus carbon to something that is relatively strong but compliant. So this is a certain type of class. And then even something that balances that. So polyethylene, for example, can sometimes have a balance between those properties. Now, it's important to point out that these are both specific values. Polyethylene is a polymer, so it's actually something that it does really well on this plot because it's light. One thing I want to mention is that you have lots of opportunities as you put in these reinforcing phases as well. So on the left is just showing an example. If I have some sort of interface in my material, as a crack is moving through it, oftentimes what happens is that the crack wants to move up and down that interface, okay? Now this can either be a good or a bad thing if you're looking at a composite, but it gives you lots of opportunities. As this crack is moving through, it's gonna meet an interface every time it hits one of these particles. So if you do a bad job and that interface is really weak, maybe it just breaks along these reinforcements. But that also is a way that you can dissipate energy. So if you have a reasonably strong interface, but it can still break a little bit, every time you come to one of these particles, you can have some crack moving a little bit up and then stopping. And every time it does that, it's dissipating energy, which is a good thing. It can toughen your material. You can also get a toughening effect from having actual phase transformations. This is really common in ceramic matrix composites. So in this example, this sample has a crack in it, and those reinforcement phases are tetragonal zirconium oxide particles. And what happens is the crack grows and the sample is loaded, there's large stresses in front of those cracks, okay? And what can actually happen is these particles will change from a tetragonal structure to a monoclinic structure. So if you remember, these are some of the isomorphs we saw for zirconium oxide. We said it can have lots of different crystal structures. The only difference is the deformation. So we can actually have that happen around the crack. Again, the reason this is good is that when this happens, the energy that's going into the system from the applied forces is going into having this phase transformation happening rather than advancing this crack. So we're sort of dissipating and wasting some of that energy in a positive way. What I want to talk a little bit about how we can start to make some of these materials. I'm just showing one common way. This is called fabrication and layup of prepreg panels. The basic idea is they're creating a resin sheet, and as they fold and make this spool of this sheet of resin, they're introducing all these fibers along a certain direction. Now, the reason that's good is that then you have fibers in given directions. You can lay these up, so you can put them together on top of each other to make a thicker chunk of material that has those fibers in exactly the directions that you want. Another way to do this is through what's called pultrusion. The basic idea is very simple. So you're still pulling these wires, but instead of going onto those sheets, it's going through a resin tank. And then this chunk of material, which is resin plus the fiber, can then be cured and pulled through some rollers to put into the right shape that you want. You can also do what's called filament winding. This is very common in things like pressure tanks. So if you go in one of the labs and you see a gas tank, that probably was made with a technique like this. It can be metal too, that's possible, but you can also find ones which are composite. And in this case, you can choose how you're winding those fiber reinforcements. Do you want it to be helical? Do you want it to be polar? Do you want it to be circumferential? It depends where you want to put those strong phases. A good example of something like this is the fuselage of an aircraft. So you want it to be strong in certain directions. This kind of looks like a pressure vessel, and in fact is a pressure vessel in some ways. And in this case, the reinforcement fibers are wound around in different ways. The last class of composites we need to talk about are what are called structural composites. So in our particle and fiber reinforced materials, you would still have a chunk of fully dense material. The difference was how we aligned that second phase and oriented that second phase inside of our material. Structural composites are a little bit different. They're basically a way of macroscopically putting together different materials to get the same sort of composite advantages. So in some sense, those reinforced sheets we mentioned, so stacking up reinforced sheets with fibers in different directions, that could be a structural composite because we're doing that on a macroscopic scale. Another good example are what are called sandwich panels. So these are relatively low density. Oftentimes they have a lightweight core, sometimes a honeycomb shape, where you can get a small weight and a large bending stiffness. So this is something, again, that is used in things like aircraft fuselage. And what happens is you have this intermediate layer. In this case, it's a honeycomb shape with lots of open space, and then some phase sheets on the top to make it so that out to the world, there's no openings, okay? This is a simple way of having a material which has a lot of open porosity in the middle. So it's relatively low density. And it's actually really easy to make. It seems pretty complicated in this upper view, but it turns out that you can make a honeycomb shape just by taking a metal sheet, putting it through something, these are called corrugated rollers, but they're basically gears, and deforming it into this corrugated sheet, and then putting these sheets together to make a panel type structure. Within this space, you can change a lot of different features. I just want to point out one important one, and that's what are the angles formed by those inner structures. So you can imagine going from anywhere from a low angle. So this is where these structures are sort of very over large distances going up and down between the top and bottom face, or having a high angle where it's a very dense network in between. And one thing I want to mention is that the big thing that can change here is what's the density of your material. You can go from something that's about 1%, something over 30%, just by changing that angle. A lot of these concepts are things that we see in nature. So wood is a good example. So if you look at wood, you find a very complex structure. There's the bark on the outside. There's these different features and rings that you find, for example, if you're counting the age of a tree or something like that. But even if you zoom into a given ring, you'll find some different types of structures. So how its structure looks different as it grows in the summer versus the spring. But if you keep zooming in, you'll also see that there's a composite structure on the cellular level. So within those cells, they're made of cellulose. You have a mixture of crystalline and amorphous material that's mixed together there. Okay? On the bottom is just showing a more real world type of view of this. This is a SEM image showing all those different pore types. There's lots of other examples in nature. A good example is the abalone shell. So this is a relatively tough and strong material. On the bottom left here, we're showing how this is actually made. It's a calcium, carbon, oxygen ceramic. And then in between, there's an organic mortar that's put together to make this sort of brick and mortar type of structure. And what's cool about that is people are using these ideas and things they discover in nature to go and make them the same type of concepts with stronger inorganic materials. So on the top right here, this is showing a way of how you could do that. You can have platelets of different ceramics. You could have little nano asperities and mineral bridges, as well as a glue type of material in there. And on the bottom, these researchers went and made these with some of these different composites. The main thing I want to point out is that on the bottom right, this is a plot of toughness versus crack extension. They were able to take relatively brittle material, so alumina by itself is just a flat line here with a low value, and make the material tougher. So it was a toughness of 30 megapascals root meter instead of whatever that is, 2 megapascals root meter. We can also see this in bone, which is a good example of a structural composite. So if you do some analysis of the mechanics of bone, you find that there's regions which experience high compression stresses, so these knobs that are sticking out. And then there's regions where you have high tensile stresses as well. And it turns out that the structure of bone is actually designed, or not designed, but it forms to accommodate these types of deformations. Okay? So these regions up here, which look like these type of honeycomb structures, they're porous, but they have a lot of reinforcement in there. Those are those high compression regions. And you can even start to see some of the extensions where you have some material to hold those tensions. And here I'm just overloading these stress fields on top. So the high compression regions have that sort of porous foam-like structure. And then the tension regions have these long elongated regions that can hold the tensile stress. In the neutral axis, where we don't have much stress, we actually have a really low density and there's not much material. You can see the difference in the mechanics of bone by looking at bones of different animals. So a human bone has near the socket, so it has this foam-like material. And then we have other things in the middle, like bone marrow, but it's pretty densely packed. Because for us, it's not all that important to be lightweight in that middle region. We can contrast that with the bone from a bird, which has a lot more porosity in that middle region. Well, that's because it's, quote unquote, engineering is different. It needs to be as light as possible so that it can fly through the air. That's its most important mode. We need to have relatively strong bones so we can run around and do things on the ground. And even those ideas of the sandwich panels that we saw, you can find in other examples in nature. So if you zoom in on a feather, the base of a feather looks like that structural composite. So it has these long barbs connected by barbules with a lot of empty space to try to efficiently make your material. And then even bird beaks look like this too. So there's empty space where you don't need strength and dense space where you do, so that animal can function in the way it wants. All right, so just to summarize the topic of composites, we often classify them in a few different ways. First, we usually describe the matrix material. Is it a carbon matrix composite, metal matrix composite, or polymer matrix composite? And then we often describe what's the reinforcement. Do we have particles, fibers, or layers reinforcing our material? And generally, what we're trying to do is balance out and correct some of the weaknesses of that matrix material. So for particle reinforced, we can estimate that elastic modulus. The properties are isotropic in all the directions because they're these small little particles. For fiber reinforced, we have to think a lot more about whether or not we're pushing and pulling along the axis of the fibers. And the properties of these materials can be either isotropic or anisotropic, depending how we put those fibers into the material. And then finally, the structural composites, we use the example of sandwich layups as a interesting sandwich panels as an interesting example of how to make structural composites. So with that, we'll finish up our lecture. I'll see you all in a Q&A session soon.